So von Neyman entropy. Let me start this lecture from calculation for Neyman entropy. We considered this problem at the end of the previous lecture. Namely, suppose that we have some message which is described by density matrix rho, and we have a problem to calculate von Neyman entropy, which is by definition is trace rho log rho. So it is some function. In fact, it is some function of rho. And here I would like to stress that in fact it is not a simple task to give definition what means function of some operator. For instance, when you write arbitrary function, we must to give additional definition what means function of operator. In fact, we can add we can add two operators. We can multiply one operator on some another operator. But what means function of operators? So there is many different possibilities to define what means function of some operator. One of the way to give definition is consider Taylor expansion of this function. So when you have some function of rho, you can write Taylor expansion, for instance, it can be written as sum over n from 0 to infinity 1 over n factorial f derivative with respect to x. Suppose here instead of rho you have variable x in 0 and then x in power n. And here we can write rho in power n. So in such definition, we can easily calculate, not easy, but here we have explicit definition what means function of some operator. Because here we have only rho in power n, and here we have only sum of different operators. So in such a way you can define what means function of operator. It is one way to define such definition, to give such definition. There is also some another possibilities, but I would like to show only one of the possibilities to define the function of operator. There is also another definition. Maybe I also consider this definition. Suppose that you can solve eigenvalue equation for operator rho in this case, and eigenstates of this operator, suppose it is E with eigenvalue, let me write here lambda, eigenvalues of this operator, and once more here eigenfunction or eigenstates of this operator rho. So you can easily then, when you have operator function f of rho, you can define, because here, let me write here, when you can solve this equation, rho can be written in such a form, sum over I, eigenvalues, and projection operator EI, I. In the eigen representation, row operator can be written in such a form. It is diagonal matrix. Let me first of all write row, then in matrix representation is the following: lambda 1, lambda 2, and so on, and here 0. It can be continued to infinity. It depends on dimension of quantum space where we consider this operator, density operator. So then we can easily define the function of operator row in such a way it will be sum over I. Here we have function over lambda I, and here projection operator EI. You can easily find that definition, first definition and second definition, in fact, is the same. It is not problem to verify that it is the same definition. It can be easy. I would like to ask you to show that really such definition of function of operator and such definition, second definition, is in fact the same. There is also some another possibilities to define what means a function of operator, but for our papers, for our next aim, it is enough to know only these two definitions, a function of some operator. In this case, it is function of density matrix. Density matrix is in fact some operator, and such function, so definition is such one. So maybe you have question concerning definition of function of operator. Але скажіть що-небудь, щоб я чув, чи ви мене чуєте, чи ні.
Та немає.
So, okay, let me also, in order to explain once more this definition, maybe you remember from quantum mechanics translation operator, which is related with derivative with respect to x. So we have exponent of operator. You remember that this operator, by definition, can be written as sum, as Taylor expansion, and here we have a in power n, and derivative with respect to x, product of n derivative, it is one derivative of order n. So here is not problem with understanding of all terms in this series. Here we have only sum and product of derivatives, so it's not problem to calculate action of this operator on arbitrary function. In such a form, when we write this without this definition, we don't know how this operator acts on function. But using this definition, you can show that this operator acting on arbitrary function gives function f x plus a, and it is just translation operator. But this result we can obtain using this definition of this operator. So, function of operator, in fact, it is not simple task, and it is necessary to give explicit definition what means function of some operator. There is many possibilities to give this definition, and here we consider two of the possibilities. This one you remember from quantum mechanics as example, translation operator, and some additional definition, but it is in fact the same definition. You can show that first definition, second is gives the same result. It is the same definition of function, some operator. Okay. So after this notation, we can consider some examples. Let me start from some examples. So example 1. Maybe we considered this example, maybe I don't remember. Okay. Suppose that you have a message which contains only 0. Quantum state of it is bit, a set of bits, but each bit is in state 0, and so on, and 0. We can easily calculate von Neumann entropy. Von Neumann entropy, let us calculate it. We can use the result which we obtain at the end of the previous lecture, namely, when you know eigen value of density matrix, so then entropy can be written as minus sum over all eigen values, depend on the dimension of this quantum space, and then eigenvalue of density matrix, log, and once more eigenvalue. So here we have a two-dimensional space, because here we have only quantum bits, so we can have here only 0 or 1, but in this message we have only 0. So it is pure state. We have a set of quantum bits in the same state 0. Therefore, it is in fact pure state. It is described by density matrix, which represent pure state 0 and 0. So eigen values of such density matrix, lambda is equal to 1, and next is 0. You remember from fundamental problems of quantum mechanics that for pure state, density matrix have one eigenvalue 1, and next eigenvalues is 0. Та я мушу телефон взяти. Секунду. Okay, so let us continue. Let's continue. So we have such message, which is described by purity, pure state with such density matrix. Eigenvalues of this density matrix is 1, and the next eigenvalues is 0. So then we can easily calculate entropy in this case for Neyman entropy. So for Neyman entropy it will be first eigenvalue 1 log 1 plus 0 log 0. In fact it is 0. Here I write expression which is not good defined from mathematical point of view. Of course, it is. We understand this as limit epsilon tend to 0, epsilon log epsilon. So it is 0. So when we write such expression, in fact, it means that here we have some small parameters which tends to 0. As a result, we have 0. Because in fact, it is not good defined, the good definition what means 0 log 0. So in order to define this expression, one of the possibility to write just such definition. But from physical point of view, we understand what it means. Therefore, it is not problem with this calculation. Okay, so for pure state, entropy, for Neyman entropy is 0. So maybe you have a question concerning definition of operators and this first example, calculation of for Neyman entropy for quantum message. It can be called as quantum message. Set of quantum bits is in state 0 or 1, but in this case, first example, we have all bits is in the same state, is in state 0. So it is pure state. This message represents, in fact, pure state. So, question, comments? Okay, so let's consider one small example. Example 2, second example. So, example, second example. You consider here, suppose that now we have a message which contains 0 and 1 with different probabilities. Suppose the next will be 1, once more 0, or maybe 0, and so on. So we have a message which contains state 0 of quantum bit with probability, how do you write, maybe P1 and, or maybe omega, that does not matter. Next, the state 1 with probability P2. Okay, maybe here it is more convenient to write, because here we have state 0, let's write here 0. It is probability which corresponds to state 0, and here we have state 1, and probability we use notation P1. I think it is more convenient to write such notation, which corresponds to state 0 and state 1. So then, as you can find that this message, in fact, is density matrix, which corresponds to mixed state. It is mixed state, and density matrix which describes this density, which describes this mixed state is the following. It is P 0, 0, 0 plus P1, 1, 1 state. You know how to write density matrix, so in this case density matrix is this one. In general, you remember from course fundamental problem in quantum mechanics that this density matrix in fact arbitrary. Okay, let me continue this example and consider more general case. We can consider also message which contains some state Q1 and Q2 and so on. Suppose Q2 and so on. So in this case, we have two quantum states, Q1 and Q2. Suppose Q1 will be with probability P1 and Q2 will be with probability P2. Then, in this case, it is not necessary that Q1 and Q2 will be orthogonal state. In general, in this case, Q1 and Q2, it not necessarily must be 0. Because in this first example, here we have two states which are orthogonal. But it is not necessary that message must contain only orthogonal states. It can be also Q1 and Q2 which are not orthogonal. So, but in this case, when we have a probability to find Q1 or Q2, then we can write also density matrix, and density matrix will be P1 first state, projection operator for first state, plus P2, Q2, and Q2. So it's very similar to this more simple case, but here only the difference is that Q1 and Q2 is not orthogonal, because here we have scalar product which is 0. So this density matrix can be considered as some special case of this one, which is more general case. So this case is more general than this one. But nevertheless, it is a two-dimensional space in first case and in the second case. So this density matrix can be written in the form of you remember this form using a Bloch sphere 1 plus scalar product sigma and 1. Sigma and Bloch vector. So depending on state and depending on these probabilities, here we can have pure state or maybe not pure state, depend on vector A. So when A equal to 0, this density matrix describe pure state, corresponds to pure state. And when A is less 1, we have mixed state. Mixed state. So in general, this message can be described by density matrix, which can be written in such a form. And now let us calculate Neyman entropy for this message with such density matrix. Before calculation, maybe you have a question. If you have no question, we can continue. Okay. So for Neyman entropy, let me write here once more. It is trace, is minus rho log rho. In order to calculate this expression, one of the way is to calculate eigenvalues of this density matrix, and because we have two-dimensional space in this example, here we have only two eigenvalues. Let me write lambda 1 and lambda 2, and then density matrix will, for Neyman entropy, will be lambda 1 log lambda 1 minus lambda 2 log lambda 2. So in order to find lambda 1, lambda 2, you must try to solve this equation. So where this density matrix is just 1 over 2, 1 plus scalar product Pauli matrices with scalar product Pauli matrices with Bloch vector. So we can easily find this to solve this solution. You remember that eigenvalue of scalar product sigma and some vector is modulo of this vector plus minus. We have here two eigenvalues of this scalar product. So as a result, eigenvalues lambda 1 will be 1 over 2, 1 plus, here we use notation, length of this vector, we notate by A, and lambda second eigenvalue will be 1 minus I. So as a result, we can easily calculate for Neyman entropy, and we obtain the following result: minus 1 over 2, 1 plus A log, and then minus so it is result for Neyman entropy in the case of this message, which is described by mixed state. So we have to find very simple result. We can verify also that in the case of pure state, pure states corresponds to the case when A equal to 1. In this case, entropy will be equal to 0, as it must be in this case. But when A is not 0, entropy for Neyman entropy, when A is not equal to 1, for entropy we obtain some non-zero result. And you can easily find that maximal value of entropy, will be in the case when A equal to 0. Then for entropy we obtain the result 1. In this case, you can write that density matrix will be the following. It will be 1 over 2, and here we have 1 plus, but because A is 0, we have 0, it is diagonal matrix. In matrix representation, it will be 1 over 2, 0, 0, 0, 1 over 2. And it is maximally mixed state. this density matrix corresponds to maximally mixed state, and we have also in this case maximal value of von Neumann entropy. This state, as you remember, when we use a representation of block sphere, so for A equal to 0, density matrix corresponds to this state at the initial of reference of frame. So, and in this case, von Neumann entropy is maximal. So, number of information which we can extract from this message is maximal. For maximally mixed state, we have message from which we can extract maximal value of information. And in this case, for one quantum bit, we can extract information which is equal to 1. Okay. So maybe with this example we can stop this calculation, and we can consider the next statement, or maybe next paragraph, which we call as relation between Shannon and von Neumann entropies. Relation. So relation. But before considering the next problem, maybe you have questions, maybe comments. So let me once more shortly to remember you what we considered. So we considered definition of entropy for quantum case. It is a generalization of Shannon entropy for quantum case, and we give definition for Neyman entropy. Then we calculate for Neyman entropy for two simple examples: pure state, and show that it is 0. The value of von Neumann entropy in the case of pure state is 0. And next example, it is example entropy for message which contains two different states with given probabilities P1 and P2, and show that in this case, in the case of mixed state, entropy is not 0, and we find also that maximal value of von Neumann entropy is in the case of maximally mixed quantum state. When using block sphere, this state corresponds to the initial of reference of frame. So, okay. So maybe you have questions, comments. Okay, so we can continue. So next paragraph. Next paragraph, relation. So between Shannon entropy, and von Neumann entropy. Von Neumann entropy. Here is very interesting, in fact, very simple relation. But in order to give this relation, let me give some explanation concerning what we means speaking about when we try to find a relation between Shannon and von Neyman entropy. So suppose, let me start from very simple example, and the most simple example is just pure state. Because we have a quantum case, we can calculate in very simple way, yeah, and we just make this calculation in example 1. And for Neyman entropy, now let me write this in such a way: for Neyman entropy, in this case is 0. You remember this result. How we can find Shannon entropy for quantum message? Of course, we cannot use Shannon formula for this message because it is quantum message. So in order to speak about Shannon entropy, in this case, we must to consider we must measure to make a measurement on this message. So in order to obtain plus or minus or 0 or 1, you must to measure this state. One of the way is to measure, suppose, so the first possibility, suppose that we measure, the idea is the following. We want to find in which state is bit in this message. In order to find in which state we have bits in this message, we must to measure the state of these bits. So we can measure these bits in using the basis 1 and 0 and 1. In spin representation, it is state arrow up, and this one is state arrow down. So when we measure state of spin along that direction, suppose that it is spin instead of 0, we have spin up with arrow up state along that direction with positive projection on this direction. So when we measure projection on that direction, what we get from this message? Result will be very simple. So we find here that state is in positive direction 1, here is one small 1, and so on. So we can message after measurement. We have a message which contains only classical bit in state 1. Of course, that Shannon entropy in this case will be 0. It's very the same result as von Neyman entropy. So once more, in order to calculate Shannon entropy for quantum message, first of all, we must to measure to find the state of quantum bit. We must to measure in what state is quantum bit. So after measurement along projection along that direction, you find that quantum bit is in the state 1, 1, 1, and so on. 0 corresponds to 1. But suppose that we measure projection of spin on some another direction. Suppose you can measure projection on x direction. Here we measure, in the first example, we measure spin in z direction, and here we measure projection of spin on x direction. what we obtain in this case. So when we have state 0, which corresponds to state arrow up, you remember from the course, once more, course fundamental problems in quantum mechanics, that in this case, when quantum state, spin quantum state is in the state arrow up, and when we measure projection on X, we obtain with probability 1/2 state in positive direction plus, and with probability 1/2, once more, we obtain probability then along that direction spin will have negative projection. It can be easy find because, let me remember this result, let me recall this result. So, eigenstatus of projection of spin on X direction is the following. It is 1/√2 arrow up plus arrow down. It is eigenvalue of sigma X with positive eigenvalue plus 1, and we have second eigenstate of sigma X with state minus arrow down with eigenvalue -1. So after calculation probabilities to find system in this state or in this state, you find the probabilities is 1/2, 1/2, 1/2 or 1/2. And we can easily calculate, in this case, the Shannon entropy. In this case, after measurement in X direction, you find that your message contains of classical bits with 0 or 1, maybe 1 small 1, 0, and so on. But probability to find 0 is 1/2, and probability to find 1 is 1/2 once more. So in this case, you can easily find that Shannon entropy will be 1/2 log with minus, sorry, here minus, log 1/2 minus 1/2 log 1/2. So as a result, we obtain it is 1. So when we measure quantum bits in X direction, you find that Shannon entropy will be maximal and is equal to 1. So it is very strange. In fact, it is not very strange. But there is some interesting properties which we can note here, that Shannon entropy depend on the measurement. When we have quantum message, and we want to use classical expression for entropy, just Shannon entropy, you can find that your result depends on the direction of measurement, which we use in this case. So when we measure this spin or quantum bits in that direction, you find that in this case Shannon entropy is 0. It is equivalently to von Neumann entropy. But when we measure quantum bits in X direction, or spins in X direction, because bits corresponds to spins, so in this case you find that Shannon entropy will be maximal and is equal to 1. You can also consider more general case, of course, but maybe considering a more general case maybe you have a question. to this consideration. Do you have questions, comments?
Поки немає.
Добре, ви давайте якийсь знак час від часу, що я вас чую, а то я говорю, я так не знаю, чи я говорю в пустоту, чи там хтось присутній, чи чують мене, чи є ще зв'язок. So, in a more general case, of course, we can measure quantum bits or state of spin 1/2 in arbitrary direction A. Suppose we have Z, X, only here must be, because it is not good, here X must be written, here is Y. X, Y, and Z. And for this case, you can also calculate Shannon entropy. I would like to ask you to consider this more general case and to calculate Shannon entropy. Shannon entropy in this case. You find that Shannon entropy will not be 0, but it also will not be 1. You find that Shannon entropy in general case will be less 1 and greater 0. And you find that when this vector will be directed along z-axis, when A will be directed along z-axis, you just find that entropy, Shannon entropy in this case, will be maximal, it will be equal to 1, and this case is just exactly equal to this one case, which we considered here. And you can find that in the case when A is perpendicular to z-axis, you find that Shannon entropy, here you find that it is 0. Here you find that it is not 1 but 0. But when this direction of measurement is perpendicular to z-axis, you find that Shannon entropy will be equal to 1. So I would like to ask you to find this general result for Shannon entropy, and result will be between 0 and 1. So our statement is the following. First of all, I would like to note that when we have quantum message, in order to calculate Shannon entropy, first of all, we must transform this quantum message into classical message. So it means that we must to make a measurement in order to find in which state quantum bits are. So using this measurement, you will find some classical message, and in this case you can of course calculate classical entropy, it is Shannon entropy. But you find, and we just now show, that result for Shannon entropy depends on the measurement. And Shannon entropy changes from 1 to 0. For Neyman entropy, always is equal to 1, because we have pure quantum state. In pure quantum state, we have no information. And of course, for Neyman entropy, in this case, must be equal to 0, and it is 0. But after measurement, after transformation of quantum measurement into classical, after measurement, you find some message which is not consist the same state, 0, 0, 0, so on, or maybe 1, 1, 1, and so on. So you have some mixing, 0 and 1, with different probabilities, and Shannon entropy will not be 0, and you find some non-zero result. So And this gives the following relation between Shannon and von Neumann entropy. Minimal value of Shannon entropy is equal to von Neumann entropy. We show this result using a very simple example, pure quantum state or message which is described by pure density matrix. And you find in this case that the minimal value of Shannon entropy is just equal to 0. So minimum value of Shannon entropy after measurement will be equal to von Neumann entropy. It can be shown also in general case, when you have some quantum message which consists of Q1 and Q2 with some probabilities, so on, Q1, Q1 and so on, and we have probabilities P1 and P2. It is also possible to find that in this case, after measurement, the task of which is to find in which state is quantum bits, you find that minimal, once more let me write this, minimal value in more general case, minimal value of Shannon entropy will be equal to von Neumann entropy. Not only for such a simple example, but in general case. After measurement, you find that minimum value of Shannon entropy is always will be equal to von Neumann entropy. So we can state that minimal value of Shannon entropy is equal to von Neumann entropy, or you can state that von Neumann entropy, it is minimal value of von Neumann entropy for quantum state which we can extract. So using different measurement on a quantum message, you can find Shannon entropy. And our statement is the following, that minimal value of Shannon entropy which we can extract from quantum message is equal to von Neumann entropy. It is a very important statement, and we show it using a simple example, but it is also possible to show this in general case. More complicated, of course, but nevertheless, the statement will be the same. So maybe you have question concerning this statement. It's a very important statement, and written here. Добре. Окей. Завтра листочку. So now let us consider the next paragraph. Properties of von Neumann entropy. Von Neumann entropy. Neumann entropy. So you know some properties from our previous lectures, very simple properties, namely that entropy for pure state is 0. So when we consider, once more, when we consider a message which is described by pure density matrix, which is pure state, so in this case entropy is equal to 0. And now we consider more complicated properties, namely first properties, is we considered. It can be the following. So for Neyman entropy, the statement is the following, the first property. For Neyman entropy is invariant under unitary transformation. So for Neyman entropy is invariant under unitary transformation. So let us consider some message which consists of state psi I with probability pi. The density matrix, in this case, it is sum over all possibilities from 1 to n. Suppose we have n different status in this message. Probability pi, psi I, psi I. Here we write definition of density matrix for this message. And now let us consider some unitary transformation. And now suppose that instead of we have another message which consists of psi I prime, and psi I prime is result of action some unitary operator on a state psi I. So let me explain once more what it means. So let me have this message. So we have psi 1, suppose psi 2, maybe psi 1 once more, and so on, psi 3, and so on. So now we apply unitary transformation to each of these pure state. So here we have state psi 1 prime, which define it in such a way. Here is here state psi 2 prime, and so on. So here we have psi 1 prime once more, and so on, psi 3 prime. So this is result. Prime means that we apply unitary operator to each of these states. Psi here we have psi 2 prime, it is unitary action, result of action, unitary operator to state psi 2. So we have some another message. After action of unitary transformation, we have a message which contains now some another quantum states, psi prime. And we have a question about von Neumann entropy in first case and in this second case. So we can calculate von Neumann entropy for this message, first message, and the second message, which is a result of action of unitary operator on this first message. So a statement is the following. Von Neumann entropy is invariant under unitary transformation. What it means? This statement means that von Neumann entropy is the same for first message and for the second one. So now let us try to show this statement. In fact, it's very simple task to show this statement. First of all, let us find a relation between density matrix which describe first first message and second one. Sorry, just a moment. Так, чуєте мене, так?
Так, чую.
Добре. Okay. First of all, density matrix row in the first case, let me write row for the first one, it will be, it is written here, it is written here. So now let us consider second case. Let me write this density matrix, use notation row prime. So it will be the following. It will be sum probability of, for instance, psi prime 1 is p1 once more. Probability is the same for all of these states, psi 1 prime, psi 2 prime, so on. So it will be p I, psi prime I, psi I prime. Now, here we can use the result for this state psi prime. It is result of action u on initial state. And for ket vector, it is written for ket vector and for bra vector. Psi I prime, it will be psi I conjugated unitary operator u plus. So we can substitute this result here for this definition. As result, you find that it will be sum over all probabilities. And here we have u prime. Here, so not u prime, u instead of this, you use this definition. And then psi I, u conjugated. So of course it can be written in this way, u, and here we have sum over I, pi, psi I, and u prime. So finally we find that it is initial density matrix which corresponds to this initial message, and you find that it is u, unitary operator, then row, and u prime. So row prime can be written using result for initial density matrix, and we have very simple relation between row prime and row prime. Once more, let me mention about this. So row prime corresponds to second message, which is a result of action of unitary operator on the first message, and row, it is density matrix which describe the first message. So very simple relation, and this relation can be used to show that in fact entropy for first and second message is the same. So let me show this. So our idea is to calculate message for the first entropy for Neyman for the first message, and for the second message. So we find that it will be the same. So S corresponds to row, and S prime corresponds to row prime. So S minus trace row log row, and it will be the same, that minus trace row prime log, so here not row prime, row, here row prime. It is equal to S prime. To show these properties, let me write identity, which can be to show in very simple way, but nevertheless, suppose that you have some function of such operator u row u prime. So it can be easy to find that it is equal to u function of row u prime. Let me explain this identity. In fact, it is identity. This operator is equal to this one. It's very important that here we can write some such identity, and this identity allows to show this property. So once more, in order to give definition what means function of operator, one way to give such definition, it is just write this function as some series or Taylor expansion. So we can write this function f of x as sum over n, 1 over n factorial, derivative is the point 0, and then x in the power n. But now instead of x, you must put this operator, and so function of this operator u row u prime, it can be sum over n, 1 over n factorial, derivative at the point 0, and here we have u f row u prime in power n. Let us consider one of the term of this sum, namely let us consider u function of row, not function of row, sorry. Here we have not function of row, but only row. So we have one of the term, here we have u row u prime in power n. What means in power n? It is product of the same operators. So it is equal to u row u prime. The next operator is the same. It means u row u prime. The next, it is the same operator, u row u prime, and so on. U row u prime. But here you can easily find that it is equal to 1, because for unitary operator, product u and u prime u conjugated u is equal to 1. It is just by the definition of unitary operator. So for unitary operator, conjugated operator multiplied by initial operator is always equal to 1. So as a result, you find that it will be u row u prime. So, and each term in this sum can be written row in power n, sorry, forget. Because here it is 1, we have row, and so on, it is row in power n. So we have very simple result. u row u conjugate in power n, it is the same that u row in power n and then u conjugate. So what it means? It means that function then function of u row u prime is equal to u function of row and u prime. Very simple, not simple. We obtain in a simple way this result, but it is very important result. This formula is true only for unitary operator u. When here we put some arbitrary operator, for instance, not unitary operator, instead of u, we don't find such result. This result is true only for unitary operator, only for the case when u prime multiplied by u equal to 1. It is important to remember that here u is unitary operator. So we find such identity, which we use for calculation entropy for two messages, and but it will be on the next lecture, of course. So with this we can stop our lecture. Time is over. We have how many? 2 times to the end of this lecture. So maybe you have a question. So at the next lecture, we use this result in order to show that entropy for first message and for message which is a result of action of unitary operator on the first message, that for Neyman entropy is the same, that for Neyman entropy is invariant under unitary transformation. And finally, we will show it on the next lecture. But now we finish it with this identity, very important for our next motion in proving this statement. So maybe question, comments. We have 1 minute for question and comments. Так, чи маєте питання якісь?
Немає.
Хочу сказати, що ви вже про це знаєте, про те, що ми далі вчимося повністю онлайн, лабораторні роботи також онлайн, так?
Так, я вже знаю.
Ось, так що я зроблю тоді вам посилання Microsoft Teams і вже там шукайте пару Microsoft Teams в розкладі. Ну, згідно розкладу, але Microsoft Teams. То коли то в нас та пара є? В середу, так? В середу. Добре, то на середу я там зроблю оголошення на ту пару. Ну, то чи маєте якісь запитання?
Немає.
Немає. Добре. Якщо нема питань, тоді успіхів, здоров'я і до зустрічі вже в комп'ютері.
До побачення.
До побачення.
Власне.
Все, щасливо. До побачення.
До побачення.